All right, welcome everyone. Today we're going to look at a new integration technique, integration by parts, and specifically we're going to see how to use this technique for calculating indefinite integrals. So first, let's just talk a little bit about where this integration technique comes from. And if we remember back, when we were talking about substitution rule, we said substitution rule really had its roots in the chain rule. So the chain rule was one of our derivative techniques, and substitution rule was sort of its integration counterpart. Well, same thing for integration by parts. It also is related to a derivative rule, and it happens to be related to the product rule. So let's just remember what the product rule actually said. It allowed us to take, if we had the product of two functions, so f times g of x, and we wanted to calculate their derivative, well, the product rule allowed us to do that. So we would do the derivative of the first function times the second function plus the first function times the derivative of the second function. And that was our product rule. Well, so just like product rule allowed us to do the derivative of the product of two functions, we also have an integration by parts formula. And this is the long form of the formula. We're going to actually look at and use more of a condensed version. But we have this integration by parts formula that says the integral of f of x times g prime of x is equal to f of x times g of x minus the integral of g of x times f prime of x. So that's the long form. We'll see a more condensed version in a few minutes. But really where you can get this integration by parts formula by really just going back up to the product rule formula and integrating both sides. And when we do that, when we integrate both sides, when we integrate this left side here, when we integrate a derivative, remember they're reverse processes, so they end up effectively canceling out. And it's specifically because the derivative is being applied to that entire left-hand side. So the integral and the derivative cancel. And that's how we get just f of x times g of x there on the left. So we have that equation, and then we move things around as needed. We won't go really too far into how to move the terms around. But really the main kind of gist of it is we start with our product rule for derivatives, integrate both sides, and on the left there, the integral and the derivative cancel out because they're reverse processes. And then we move terms around as needed until we get our integration by parts formula. All right. So let's look at the more condensed version. This is the formula that we're going to be using. So it says the integral of u dv is equal to u times v minus the integral of v times du. So this is the one we'll refer back to most of the time. And we're going to think of integration by parts kind of like what we did for substitution rule. We're going to think of it more as a process. So the first step of that process is to choose u and dv. So that's the first step. So kind of like substitution rule, we had to choose u. Well, same thing for integration by parts, except now we're kind of deciding on two things, u and dv. Once we decide u and dv, the second step is to calculate du and calculate v. So how do we calculate du? Well, there we're going to differentiate. So we're choosing u, we're going to differentiate u to get du. Now if we're choosing dv, how do we think we get back up to v? Well, we're going to integrate that. All right, so that's step two. Step 1, choose u, dv. Step 2, calculate du and v. And we calculate them by differentiating and integrating accordingly. Now the third step, this is where we actually kind of just plug everything into this integration by parts formula. So way to kind of help remember this formula, if you use this grid setup of u dv and duv, if we multiply these two terms along the top here and integrate, that's the left-hand side of this equation. And then what the integration by parts formula says is that integral, the integral of u dv, is equal to u times v. So we kind of multiply down the diagonal there. And then we subtract and integrate the v times du. So all of the the way to remember the formula, you kind of get this backward Z shape, and then all the horizontal lines there are where we actually integrate. Or maybe just remember the formula, but that's one way to remember it, is with that backward Z shape. So integration by parts, the actual formula is the integral of u times dv is equal to u times v minus the integral of v times du. Step 3 is to plug all the pieces that we've calculated and picked, plug it into that formula, and then step 4 is to finish integrating. So when we look at this formula, you might be thinking, well, how is this going to help us? We have an integral on the left, we have an integral on the right, we're not really getting anywhere. So step 4 is to finish integrating that integral on the right. And the reason why this technique works is how we pick u and dv. The integral on the left is usually the complicated integral that we're trying to do. And the integral on the right is usually easier. Well, it hopefully will be easier because we need to be able to do it. So effectively what we're doing is we're taking a complicated integral problem and producing a new integral problem that's hopefully easier for us to do. All right, let's try an example. Let's see how this process works. So we're going to integrate the function x times e to the x. And we'll kind of just go through the process without really explaining why we choose u and dv, why we make those choices. We'll kind of go through the process, see how the calculations work first, and then we'll go into, why are we picking u to be this and why are we picking dv to be that. So let's just see how this is going to work. So step 1, we want to pick u. And for this one, we're going to pick u equal to x. Again, we'll see why we do that a little bit later. And we'll pick dv to be e to the x dx. So that's step 1. Step 2, we're going to calculate du and we're going to calculate v. So to get du, this is where we differentiate. So we're going to differentiate that x term, it's just 1, and then multiply by dx. So it'd be 1 times dx. We don't normally write multiplication by 1, so we'll just put dx. Then on the right side, we're going to calculate v, we're going to integrate e to the x. And the integral of e to the x it's a nice one. It's its own antiderivative. So the integral of e to the x is just e to the x. So again, here we're differentiating, and over here we're really integrating. And that's how we're calculating du and how we're calculating v. All right, so we have step 1 and step 2 done. We've chosen u, picked dv, calculated du, calculated v. Now we want to plug all of this into the formula. So what does the formula say? Let's just write it out again. Doesn't hurt to do that. the integral of u dv is equal to u times v minus the integral of v times du. So the integral that we're trying to do is right along the top there. It's the integral of u times dv. That's the one we're trying to do. So what that integral is equal to, it's equal to u times v. So we multiply those terms along the diagonal. Let's write that out. X e to the x. So we're just multiplying u and v together. And then it's minus the integral of v times du. And the integral of e to the x times dx. So that's step 3, is to just plug all those pieces that we calculated in steps 1 and 2. We're plugging them into the integration by parts formula. So really this is our u times v, and this is our v times du. We're just plugging those pieces in. Now, we still have a little bit more. There's still an integral on the right-hand side that we need to do. So we still have to do the integral of e to the x, but that's an easy one. That's one we just know. So you can kind of see the integral we started with was much more complicated, and by using this integration by parts formula, we end up with an integral on the right that's easier to do. So the integral of e to the x, that's just something we can do. And so step 4 is to just finish it off. X times e to the x, and then the integral of e to the x is just e to the x. So we have minus e to the x there. And again, we're doing an indefinite integral, so we put our usual constant there at the end. And that's step 4. All right, so that's really how the process works. It's picking u, picking dv, calculating du, calculating v, plugging into the formula, and then keep going. All right, so let's talk a little bit more about how we pick u and how we pick dv. So, you might be wondering, why did we pick u to be x, and why did we pick dv to be e to the x? And so, there's various strategies on how to do this. Sometimes they work, sometimes they don't. Kind of like what we saw with substitution rule. But the kind of the two strategies to keep in mind, and we'll talk about the second one in a second, is we look at the parts of our function. So our function, what was our integral in example 1? It was the integral of x times e to the x dx. And so when you're trying to decide what to pick for u and what to pick for dv, you want to kind of break your function apart and kind of write it as two separate parts or pieces. So in this case, I would consider x and e to the x. Those are the two parts of my function. And so kind of one of our strategies and I call it the meta strategy because it doesn't give too much specifics, but we generally pick the u term, or we look at our two parts there, and whichever one simplifies the most when differentiated, that's usually what we pick for u. So if I were kind of just considering these two, which one should I pick for u? Well, differentiating x gives me 1, so that simplifies a bit. Differentiating e to the x doesn't really simplify at all. The derivative of e to the x is just e to the x. So this part of our function simplifies more when we differentiate it. Now, with that in mind, a strategy for how to pick dv is we look for the term that is easy to integrate. And so going back up, x, that's not too bad to integrate. E to the x, that's also not too bad to integrate. So based off of this strategy, I would think the fact that u, or the fact that this part of x really simplifies when we differentiate it, that would lead me to choose u equal to x, because that'll simplify the most when we differentiate it. And then once you pick u, your hand is kind of forced, and what you pick for dv has to be the other part. So I'm picking u equals x because this simplifies when differentiated. And then as soon as you pick what you think u should be, then the other piece just goes to dv. Or maybe you pick dv, and then whatever you didn't pick, that would go to u. So as soon as you choose one of the pieces, the other piece has to go to the opposite one. All right, so this is sort of the overarching strategy for how we're doing things. Let's get a little bit more specific, and we use an acronym to help us remember, how to choose u and how to choose dv. Again, this usually works, but there might be some cases out there where this strategy, doesn't quite work. So we have to revise things a little bit. But the acronym is LIATE. And, what it stands for is the L stands for log functions. The I stands for inverse trig functions. A stands for algebraic. Things like power functions or polynomials. So things like x squared or, 2x plus 3. Power functions or polynomials. The T stands for trig functions, sine, cosine, things like that. And then E stands for exponential functions. And so the way we kind of remember this acronym is the pieces of our function that are higher up, this is what we generally pick for u, and the ones down here, lower on this list, those are the ones we generally pick for dv. So how we actually use this strategy is, again, let's kind of talk about it in the context of example 1. What was example 1? It was x times e to the x dx. And again, let's break this apart, break our function into two parts, x and e to the x. And then we classify each of those parts of our function into one of these 5 categories. So if I were looking at this x term, that's a polynomial. That's a power function. That's an algebraic function. And same thing, we do it for the other one, e to the x. Well, that's an exponential function. So I have my algebraic function on my list for example 1. I have my exponential function on my list. And what we pick for u, the term that we pick for u, is whichever one is higher. So my algebraic function, x, is higher on this list than the exponential. So that's what we would pick for u equal to x. And same thing, dv then is going to be the e to the x because it's lower on the list. And so that's how we can use this strategy. We remember the acronym, and the L term, the things higher up are what we choose for u. The things lower down are what we choose for dv. And there's some flexibility here. So, you can play around with the ordering a little bit. So log functions and inverse trig functions, you could switch the order of those. Same thing with trig and exponential functions. You could switch the order around there. So, a similar acronym that might be a little bit easier to remember is ILATE. So you do the inverse trig functions at the top, then log functions, and then it's similar. Yeah, and whichever one you like better, whichever one you remember better is fine. So in the inverse functions, and really the difference here is log functions are really in an inverse function. So the ordering for those two really doesn't matter. All right, so that's a nice strategy, a nice way to help us remember how to pick U and dv. So let's try it out. Let's try another example where we're going to use this strategy to help us with it. So let's try out example 2. We're going to integrate the function 2x plus 5 times sine of 3x, and we're going to use integration by parts. And one of the tells that we want to use integration by parts is a lot of times we see a product. We know it's related to the product rule. We see a product there right in the middle. It's 2x plus 5 times sine of 3x. So that's a sign that we might want to use integration by parts. All right, so let's start. Step 1, we want to choose u and calculate and choose dv. So this is generally the hardest part of the problem here. And so let's kind of write down the two parts of our function. We have 2x plus 5 and sine of 3x. Those are the two parts of our function. Now, 2x plus 5, that's a polynomial, so that's an algebraic function. And then sine of 3x, well, that's a trig function. And if we remember our acronym, algebraic functions are right there in the middle. Trig functions were right there. And kind of on this continuum, if we do it horizontally, things further, the part of our function that's further to the left is what we pick for u, and the things that are further to the right are what we pick for dv. So looking at this, my algebraic function is further to the left on our little list there. So that's what I'm going to pick for u. And the trig function, the sine of 3x, is further to the right. So that's what we pick for dv. So it'll be sine of 3x dx. All right, so that's the hard part. Choosing u, choosing dv. All right, now step 2. Give myself a little more room there. We're going to calculate du and calculate v. And we're starting with u. U is equal to 2x plus 5. To get du, we're going to differentiate. So derivative of 2x plus 5 is 2, and then we multiply by dx. And then over here, starting with the differential dv, to get v, we're going to integrate. So we want the integral of sine of 3x. So the integral of sine of 3x is negative 1/3 cosine of 3x. And we're going to see these types of things a bit. So it's helpful to remember, kind of call these like k-forms. So the integral of sine of k of x, where k is a constant, is equal to negative 1 over k cosine of kx, plus c in general. So where we have that constant, it's sine of a constant times x, or cosine of a constant times x, or there's one for e to the kx. So these are some k-form integrals that we'll see a bit. So it's a good idea to kind of have those worked out. If you don't remember those, or if you don't see where they come from, you could do a u substitution to get that formula. So you'd let u equals k times x and go from there. We'll probably talk about those a little bit more later on, but for right now, let's kind of get going with the integration by parts here. So the integral of sine of 3x is negative 1/3 times cosine 3x. We have all our pieces now, so the next step is to go through the integration by parts formula. So the integral we want is u times v. That's the one we're trying, u times dv. That's the one we're trying to do. So we know that's equal to u times v. So multiply those terms along the diagonal. So we get 2x plus 5 times negative 1/3 cosine 3x. Then we subtract and we integrate, and then we multiply those v times du, those terms along the bottom there. So when we multiply those together, we get negative 1/3 times cosine of 3x times 2. And you know what? I'm going to put the 2, I'm going to multiply the 2 with the 1/3 just so we can consolidate our constant terms. And then we have our dx. So when we multiplied the 2 times dx and the v term here, those constant pieces in front, the negative 1/3 and the 2, it helps to just kind of consolidate those as you go. So we end up with negative 2/3 when we multiply those together. All right, so that's step 3. That's our integration by parts formula. We see that we still have an integral on the right side there, but now this is one we can do. This is one of our basic K-form integrals. And that's what we do. We keep going with the integration. So for this piece right here, we're done with that. We're completely done with that. So maybe clean things up a little bit. I might put the negative 1/3 in front. So 2x, negative 1/3 times 2x plus 5 times cosine of 3x. And then we want to do the antiderivative of that cosine 3x term. So we're going to get plus 2/3, and then the antiderivative of cosine 3x is 1/3 sine of 3x. And then we put our plus c at the end. So that's step 4. Finish the integration. So this piece right here, we were done with that. That was the u times v term, and we were done with all integration there. And then all we needed to do was find the antiderivative of cosine 3x. And that's what we're seeing right here inside the parentheses. The antiderivative of that is 1/3 times sine of 3x. And there we go. We have our antiderivative. You know, maybe there's a little bit more cleaning up we could do, but that's fine. We could stop there. All right, so really that's the foundation. That's what we need to be able to, you have enough now where you can go through and basically do any integration by parts problem that you want. Tomorrow we'll see just a few more examples because there are some sort of trickier ways to pick u and dv. So we'll see a few of those tomorrow. So yeah, but you have enough now where you could probably go through and do some serious damage on the homework. All right, so let's stop there, and then we'll do some more examples tomorrow. All right, we'll see you then. Bye-bye.